Hello, everyone. In this video, I'm going to introduce you to a concept known as heaps. A heap is another binary tree, but it has a certain property. In this particular case, what you see on this slide is an example of a minimum heap. A minimum heap means that the root node has the smallest value of all nodes in the heap. And for any node, its children nodes have larger values than it does, like this heap in this slide does. 2 is the root. Its children are 5 and 6. Both are larger. In the case of the 5, its children are 9 and 7, which are larger than the 5. So this binary tree in this slide is a heap. A heap is also a complete binary tree. The author tries to go into a mathematical explanations of what that means. Here in my code, I have a more plain English version of that. So a complete binary tree means the following. All levels except the last level must be completely filled with no gaps. So as you can see in this tree on the slide, there's your root node. The next level down should only have 2 nodes, and it does. The level where the 9 and 7 are is the last level. It does not have to be full. But the other condition is this. The last level is not full. It must have nodes at the leftmost positions. And as you can see, that is true of this example. Here's the last level. Not completely full with 4 nodes, but the nodes it does have are all the way to the left. So for example, if the 7 was not attached to the 5, if it was attached to the 6, this would not be a complete binary tree. Now, as far as levels, height, okay. Levels typically begin at level 0. So the root's at level 0, the root's children are at level 1, etc., etc. The height of a tree is the number of levels it has. So as you can see, this particular tree has 4 levels, 0, 1, 2, 3. Our heap has 3 levels. Here is level 0 where the root is. Here we have level 1, and then here we have level 2. Now, a binary tree with n levels can have roughly 2 raised to the n nodes. So if this heap were completely full, we'd have 7 nodes, which is roughly 8. And so in general, we can say that a heap storing n keys or nodes has height O of log n. Keep in mind that is log base 2 of n. So if you have 8 nodes, your height is log base 2 of 8, which is equal to 3, roughly. Okay, now you can insert a node onto a heap and you can remove a node from a heap. This video will show how to insert a node onto a heap. Removing a node from a heap will be in part 2 video for heaps. When you have a heap, the way you insert a node is you always put it at the first open position. So you're going to go down to the last level and you're going to put a brand new node at the first open position. So for example, in this heap that we had before, we want to insert a node that contains a 1. So that 1 is going to go here. Level 1 is completely full. We can't put a node there. But level 2 is not completely full, and there is the first open spot. So currently the 1 is attached to the 6th, but we don't have a complete binary tree or a heap at this point because this is a minimum heap. And that means the smallest value needs to be in the root. The smallest value is now 1, and it's clearly not at the root. So what we're going to do is we're going to do an up heap, also known as bubbling up. What you're going to do is you're going to compare the node you just inserted to its parent. And if the node you just inserted has a smaller value than the parent, you're going to swap those two nodes. So for example, if you recall, the 1 was placed here on level 2, and its parent was a 6, but 1 is smaller than 6. So right here, we're going to swap those two nodes, the 1 and the 6. So here's where we are. Now, the 1 is where it needs to be. Now you compare 1 to its parent, which is now the root, which is a 2. And 1 is smaller than 2, so we will swap those two nodes. So you can see where the term bubbling up comes from. You're going to keep moving the brand new node as high up as is possible in the heap until it's in its proper place. As I said, removal from a heap, we'll cover that in a second video. Now in the code, what we're going to do is create a maximum heap. This will work the opposite of what we saw in the slides. A maximum heap means the largest value is at the root. And for any node, its children are going to have smaller values than that node. Once again, we're going to use a list instead of a linked list to demonstrate this. So what I've done in the constructor of my max heap class is I've created a list named heap and a variable named size, and I initialize it to 0. Now, these three methods that you see right here will help us in building this heap. The first one is getLeftChild. This returns the index of the left child of a node. We have one parameter, which is the index of that node. The value of the left child's index will be this, 2 times index plus 1. One thing you must be aware of, we're assuming the root node has an index of 0. This is how our textbook's author decided to approach this problem. Some people like to have the root node be at index 1 rather than index 0. I'll admit that does make the math a little bit easier, but just for consistency's sake, since our textbook decided to put the root at index 0, I'm going to do that too. So for any node, its left child, the index of that left child can be calculated with this formula. Furthermore, if you want to get the right child, index of the right child of a node is this formula, 2 times index plus 2. And if you want to get the parent of a node, given its index, it's this formula, index minus 1, and then divided by 2. But if you'll notice, we have 2 / symbols. 2 / symbols are Python's version of integer division. So if you do division in Python and you put 2 / into the equation, you're doing integer division. That means you will only get the quotient and you will not have a decimal point attached to that result. Now, when it comes to swapping nodes or swapping values in the list, this is where Python makes things much easier. Here's how you define a swap function. Parameters are the 2 indexes that you want to swap. All you have to do is set up this equation. Heap at index 1, comma, heap at index 2 is equal to heap at index 2, comma, heap at index 1. This were Java or C++, we need to define a local variable in this function to be able to swap values in a list. But in Python, you don't need a local variable. You can swap two values with this formula that you see right here. That's why Python's really cool. All right. So when it comes to inserting a new value onto a heap, here's the procedure. The first thing you're going to do is take the value that's going to be added, that's what the value parameter is, and you'll use the append function to put it at the end of the list. That's the first open slot in the heap. So the append function will put the new value at the end of the list, which is also the last node of the heap. Then we're going to create a local variable whose name is current. We're going to set it equal to the length of the heap minus 1. That will be the index of the value we just added. The variable current is going to be the index of the value we just added. And now here's how we're going to go through this. So now we set up a while loop. This is where we're going to move the new node eventually to its proper position in the heap. So in this while loop, we have first condition, current greater than 0, meaning it's a valid index. And the value at index current is greater than the value at the parent of current. If both of those conditions are true, then we go into the while loop. Because remember, this is a maximum heap. So if those conditions are true, here's what we'll do. We will call the swap function. The first index we'll send it as current. The second index is the parent of current. That will flip-flop or swap those two values. And then in the while loop, we will redefine the value of current. We'll set current now equal to its parent if we were able to reverse the two values. And then when the while loop is finished, we increase the size variable by 1 because we have a brand new node in the heap. Now here in main, I'm going to run the entire program, but I'm only going to focus on the output for this part right here, where I create the heap by making an object of the class, and then I will insert these 4 values onto the heap, and then I will print it. And then after I do that, I will insert a 100, and then insert a 75. Let me run this program and show you what I get. So let's focus on just the initial heap. So there is my initial heap. So what this looks like, if you were to make it in node notation, is this. You'd have a 99 right here. And you'd have 72 there. 61 would be here. And 58 would be there. All right. Notice that the order of the elements in the initial heap is not the same as the order in which I inserted them. That's because what's going on is each time a node is inserted, we're seeing if we need to swap it. So that means our list is like this. Okay. There's 99 and 72, 61, and 58. That's supposed to be a 58. I'm sorry. So again, my artwork is so outstanding. It'll have to do at this point. Okay. Now then, let's just run through what happens when you insert the 100. Okay. So when the 100 is inserted, the first thing we do is we append this to the list. So we put the 100 in the first available slot. That would be right here in the list. We might as well do this as well. So the 100 is going to go right here. Okay. So that means that here in my insert function, so remember, current variable is going to equal the length of the heap minus 1. The length of the heap is currently 5, minus 1 is 4, so current is 4. That's the index of the 100. That's what current is equal to right now. So now we'll say while current is greater than 0, which it is, and the element at current is greater than the element at the parent of current. Well, the parent of current, if you take 4 and divide it by 2, you get 2. No, I'm sorry, you take current minus 1 and divide it by 2. That's right. Okay. So that's 3 divided by 2, and that's a 1. The parent of current is 1. That's the 72. Well, 100 is definitely bigger than 72. So we need to swap those. So that means the 72 and the 100 will switch positions. The 100 goes there. 72 goes there. That's a 72. Just take my word for it. So put the 100 here. The 72 there. Okay. And then you change the value of current. Current is the parent, so now current becomes a 1. 1 was the parent before we did the swap. So current is now set to 1. Okay. Well, now in the while loop says, well, current is bigger than 0. It is. And the element at current is greater than the element at the parent. Well, the parent is now current minus 1, that quantity divided by 2. Well, 1 minus 1 is 0. So the parent is 0. That's the 99. And the 100 is bigger than the 99. So guess what? It's time to swap the 100 and the 99. Do it first in here. So the 100 goes there. 99 goes there. And in the list is there. 99 is there. And despite my wonderful artwork, you'll notice that the elements in this match the elements in this. There you have an example of how you bubble up or up heap to insert a value into a heap. I know I've said this before, but I'll reemphasize it one more time. We will cover removing a node from a heap in a separate video, Heaps Part 2. If you have any questions, please send me an email at kmuldrow@lbcc.edu.